we're still solving. It's just sometimes now, like, if you look at this one, we have a mixture of cosines and sines. So you're going to get your reference sheet again, and you may have to use stuff from this as is necessary. So this is the little handout I gave you for your last test. I know. I'll give you one. They're on your old note packets. I'll have to look back and see where we have all this written, but they are on your old notes. Your reciprocal functions, you know, your Pythagorean identities, I'll show you where those are on your notes, and your double angles. So this one right away, cosine of 2x and a sine. As soon as you see 2x, you should be thinking double angles. The thing with the cosine of 2x is you have three options that you'll remember. You've got to pick which one is going to be best for your particular equation. Now, I would say since our equation has a sine in it, you're best off replacing this with the sine version, just so it's all consistent. Okay, so I'm going to take out the cosine of 2x, and I'm going to replace it with 1 minus 2 sine squared of x. Then there's the plus 2 afterwards equals sine x. And then this is like a quadratic. We have a square term, we have a regular term, and then we have some constant. So I'm going to bring everything over to the same side, subtract the sine x over. And then 1 plus 2 gives me 3. So there it all is, equaling 0. I hate when the leading coefficient is a negative, so I would just divide both sides by -1, which will just change all the signs. And then with a quadratic, you have two options. If it's factorable, I would factor it. If it's not factorable, you have to do the quadratic formula. So, is this factorable? Good. So we have 2 sine x and sine x, for sure. We'll make 2 sine squared. And then to make 3, it's either 1 and 3 or 3 and 1. But I need to play around so that my outer and my inner makes positive 1. So that's going to be 3 here and a 1 here. So my outer is 2 and my inner is 3. And 3 sine x's, so there's my positive 3 sine x, minus 2 sine x makes 1 sine x. So far, so good? Really, after that substitution, everything else is the same as what we've been doing. So now we'll just tee it up. And so on this first factor, what does sine of x equal? If I tee that up, I have to subtract 3 and then divide by 2. So -3/2. We should love that because, well, more than just it's not on our chart. It's not between -1 and 1. It's out of range, so you're going to get no solutions for that one. If you didn't realize that and you did inverse sine of -3/2, you'd get an error. Right? And that's how you know it's no solutions. On the second one, sine of x equals 1. So if you use the unit circle, which I still have up there, sine is your y coordinate. When is your y coordinate 1? At what angle? 90 degrees, but this is in radians, so pi over 2. And that's the only time, right? So x equals pi over 2. And that's your only answer. So here's one, we have only one answer. You could have up to 4 answers, 2 solutions from the first teeing it up and 2 solutions from the second teeing it up. Good? Okay. Second one, already all in terms of sine, but still, they're not taking the sine of the same thing, so I can't combine like terms. Sine of 2x is another double angle. I'm going to replace that, sine of 2x, with 2 sine x cosine x. So taking this out and replacing it with 2 sine x cosine x. minus the sine x that's there equals 0. So, is it factorable? It's not a typical quadratic because there's not something squared. There's a GCF of sine. Good. So if I take out a sine x, I'm left with 2 cosine x minus 1. If I tee this up, the first factor, sometimes people overlook this and don't treat this as a factor. It is, your GCF is still a factor. So the sine of x could equal 0. And your second teeing it up is going to say that the cosine of x could equal positive a half. Good. So for the sine of x equaling 0, just look at your circle over there on the whiteboard. When is the y coordinate 0? And keep in mind we're in degrees. 0 degrees and 180, right? On both ends of the x-axis, so 0 degrees and 180 degrees. That doesn't happen when sines and cosines equal 1, but it does happen when they equal 0. And then as far as cosine being positive, which 2 quadrants are we in? 1 and 4. So we have to find some angle there where cosine is positive and some angle there. And in order to get those, what's our reference angle? So look at, on my red circle over there, look at where cosine, meaning the x-coordinate, equals a half. 60 degrees, which is, oh yeah, we are in degrees, so 60 degrees. So this is what? 60, what's this? 300. Does everyone follow that? Okay, around our rotation, a full circle would be 360, but that's 60 degrees too far, so back it up 60 and you get your 2 answers of 60 degrees and 300 degrees. Oops. All right, last one. Oh, Mrs. Frazier, really? You're going to make me teach them this? All right. No. What? Well, this one doesn't have an angle replacement. These are all double angles. That's why. So I can't just take out the 1/2. Here's, first of all, she's got a little bit of an inconsistency here. If you use an x in the equation, this should really say that x has to be between 0 and 360. Okay? So the issue is we're taking the cosine of half of x, but our interval is what x can be. So if x has to be between 0 and 360, what does half of x have to be between? 0 and 180. That's a key part. If x has to be between 0 and 360, then half of x has to be between 0 and 180. You can thank Mitch for making it boil. Yeah, that's what that is. Okay, so essentially, as far as the solving part, this is much easier than the rest. We don't really have to do anything. But we're not figuring out what x might equal. We're finding out what half of x could equal, because the cosine of what equals 1? Look at your red chart. What degree is it when the cosine equals 1? 0 degrees, right? So this half of x could equal 0 degrees. Yeah, because we're going to solve for x now. We're just going to divide both sides by a half and get x equals 0 still. So the difference is with these others, and just to kind of so that you see this, They started as double angles, so we could work that out, and it was all just sine of x, sine of x. So we would set x equal to our important numbers and be done. Sine of 2x, we substituted out. We had sine of x equals cosine of x. It was always x equals. So we could jump right into what our answers were. In a case like this, when we find from our red chart over there what our values are, where cosine equals 1, it's going to be half of x equals those things. And then you're going to have to solve for x beyond that. So I'll give you another quick example that's going to give you more than one solution. If I said the cosine of a half of x equaled negative root 2 over 2. What angle is the, well, first of all, what quadrants are we in? When cosine is negative. When cosine is negative? 2 and 3. When cosine is negative. But now it's half of x is what's going to equal these things. So what is the reference angle for root 2 over 2? Let's go in degrees. Okay, so if you look at your red chart, cosine is your x coordinate. When does your x coordinate equal root 2 over 2? Is at 45 degrees. So 45 is our reference angle. So this one will be 180 minus 45. And this one will be 180 plus 45. So here's the thing. X would have to be between 0 and 360. So half of x would have to be between 0 and 180. Yes? And when we find these two answers, this is what half of x equals. So half of x equals 135, or half of x equals 225. And it's just that additional step of dividing both sides by a half, aka multiplying both sides by 2. Which will make this 270, and we'll make this 450. And this one is out of range, right? X can't be 450. X has to be between 0 and 360. 1/2 x does. That's why that one also wouldn't work, because a half of x was already over 180, which is what makes x itself over the 360. No, it wouldn't. No. That's a little thing because of the fluctuation of the period here, but we don't have to get into that. All right. Please tell me that's it. Oh. No, it isn't. Really quickly, because you're going to need these identities. And again, this is the spiral question that someone asked. So there's two ways you could do that. With cosecant squared, you could use this one and replace it with cotangent squared plus 1, which I think is a great idea, because if I replace that with cotangent squared plus 1, I'm then just going to subtract the cotangent squared. Do you follow? So cosecant squared is the equivalent of cotangent squared plus 1. But then there's the minus cotangent squared, and those will cancel. So this just ends up being 1 over cosine, which is secant of x. Another way of doing that same problem, if you didn't recognize that, which a lot of you might not have, cosecant squared is the same as 1 over sine squared. Cotangent squared is the same as cosine squared over sine squared, all over cosine x. But this just immediately gets uglier because you have a complex fraction. But you have, your numerator is 1 minus cosine squared over sine squared, all over cosine. And 1 minus cosine squared, that should, 1 minus cosine squared is going to be the same as what? Sine squared. So you'd replace that with sine squared over sine squared, which would just be 1 over cosine, which is secant. It's just a lot uglier if you don't recognize that Pythagorean identity that we did the first time. Sine of pi over 4. Look at your red chart over there. What is the sine of pi over 4? What is the y coordinate? Radical 2 over 2. The cosine, now the reference angle is pi over 4, and the cosine of that is also root 2 over 2, but what quadrant is 3 pi over 4 in? The second. And is cosine positive or negative there? Negative root 2 over 2. So this would just be negative 2 over 4, which is negative 1/2. And then the last one on the spiral that you guys asked about, log base b of b is just, no, well, log base b of b to the 4th is just 4, because technically we can take that out in front, right, 4, and then log base b of b is just 1, so it's 4 minus 1, and that's just 3. I put 2? Oh, I lied. No wonder you had a question on it. 4 minus 1 is 3. It was a rough day. And that was before the mailbox incident. This is bad thing last week. Oh, funny. All right. And who were you? Okay. Okay. All right, let's look at Carolina's number 3. She gets it equal to 0. She has an A of 9, a B of negative 6, and a C of negative 2. So the first thing that's wrong is your quadratic formula. It starts with the opposite of B. So if B is negative 6, that should have been positive. Plus or minus the square root of B squared minus 4AC all looks good. Your discriminant looks good. It's just that's a positive 6. That's going to throw off. Ooh, that also shouldn't be negative. I'm sorry, your discriminant is not right. If you type in 36 minus 4 times 9 times negative 2, it's going to be a positive 108. So 6 plus or minus root 108 over 18. And so you get your 2 decimal answers. Okay? So you get cosine theta equals one of those decimals, and cosine theta equals the other one of those decimals, whatever you get when you do 6 plus root 108 divided by 18, and then the 6 minus version, and then inverse cosine of that, and inverse cosine of that. Right. And then really, this is the hard part. Because this calculator is only going to give you the reference angle. And then you have to find the 2 quadrants that have that reference angle. So the hard part really comes down here. Just the mentally tough part. Because it's not work I can really show. You just have to listen through the explanations. Okay, so your homework. Oh, I do have it, Tommy. Here you go.
I just said
your homework will be the odds. What did you say?